Welcome to Astronomy Zero lecture. Here, what we are trying to do is we are going to learn to look at the sky and get ourselves familiarized with various features of the night sky. So, since we are under lockdown right now, I have decided to use an astronomical software which may be of use to many of you. I strongly urge you to use this particular astronomical software, which is called as Stellarium, which is freely available to anybody who wants to use it. So, using the Stellarium, I have decided to explain to you how night sky is and what are the various things which you can observe in the night sky. So, right now I have set the place as Bangalore, which is at a latitude of basically nearly 13 degrees north and 77.5 degree to the east of the Greenwich meridian. This particular software right now is showing you a field of view of 60 degrees. That means if you measure the distance from here to here, it will it will show you an angle of 60 degrees basically, and the date is 20th June, and we are at about 5:30 p.m. in Indian Standard Time, which is ahead of the Universal Time or Greenwich Meridian by 5 hours and 10 seconds according to what is set here. Okay. Now, one of the first things which you should wonder about is why can't we see stars during daytime? Many of you will say that it is due to the presence of sun. That answer is only partially true. One of the major reasons why you cannot see stars during daytime is the presence of atmosphere. For example, the light from the sun strikes the gas molecules in the atmosphere and scatters the light, and that scattering is called as Rayleigh scattering, and the Rayleigh scattering is the main reason why the sky appears to you as if it's blue. So if I remove the atmosphere, then even during daytime stars will be visible to you. So this software actually permits you to remove the atmosphere. So I'll remove that, then immediately you will be able to see the stars. And the most wonderful sight, which none of you would have seen, is the sight of the Milky Way. If you can see this haze around the sky, that haze is basically our galaxy's disk, which is called as the Milky Way galaxy. And the other thing which you notice out here is basically the cardinal points. For example, south, southeast, southwest, etc. are shown in this diagram. In this simulation. So we have to keep track of all these things. Now, one of the usual questions which I'll ask my students is where does the sun rise? So everybody will think that it's very obvious. Sun rises in the east, but that answer, if you think about it a bit carefully, is true only if you are stationary on the surface of the earth. If you are stationary on the surface of the earth, then you will see that sun rises on the east. Now, why does that happen? Because earth rotates from the west to east. Now, the second question I'll ask is, does moon rise? That I will not answer to you right now. You will have to think about it for some time, and I will be very eagerly awaiting your answers. The third question I'll ask is, do stars rise and set? So many people will answer yes, stars will rise and set. So stars usually rise in the east and stars will set in the west. So just to demonstrate that, I will speed up the rotation speed of the earth, because this software allows us to do that, then you will easily see that the stars are rising in the east, and if I turn myself to the west side, you will be able to see stars are actually setting in the west. So stars also rise and stars also set. Now let's get back to the basic position once again. We will rotate ourselves back to the east. Now the position change of the stars as a function of time gives us a small problem. The problem is, if you make a new discovery in the celestial sphere about maybe a star or a new phenomena happening in the sky, how will you convey the position of that object to somebody who's somewhere else, say in the USA? If that person is standing next to us, immediately you will be able to point it out to them and then say that that object is right there. For doing that, we will be using a coordinate system called as azimuthal coordinate system or alt azimuth, as the case may be. That will look like this. So you will see that you can see the analogous to the longitudes on the surface of the earth. You will see lines like going from top to bottom. The origin of that point is basically here. This is going to be called as the zenith point. Okay. Now zenith point is one of the reference points, and you will also see that the north pole, the equivalent to the celestial longitude, from the north side, if you consider a great circle passing through the zenith, that will have an angle of 0 degrees. Now it will go 10 degrees, 20 degrees, 30 degrees, etc. towards east. And if you go a full circle and come back, you will again see that the angle out here is 350 degrees and 360 degrees, which corresponds to 0 degrees. So there is a azimuthal angle which we measure from the north point in the eastward direction, and then analogous to your latitudes, you will have basically 10 degrees, 20 degrees, 30 degrees, and so on. And when you reach the zenith, the angle will be corresponding to this line. This circle will be corresponding to 80 degrees, and zenith will be exactly equal to 90 degrees. I hope it is clear to you. But this particular coordinate system is a totally useless coordinate system, except in pointing the telescope, or if your friend is standing right next to you, to explain the position of some star or the other. But even more useful coordinate system is something which is called as the equatorial coordinate system. I have shown it here in the blue color. Now this equatorial coordinate system is basically the projection of the Earth's longitudes and latitudes onto the sky. Okay, so to understand that, imagine that Earth is like a transparent sphere on which you have actually drawn the longitudes and the latitudes, and put a bulb at the center of the Earth and shine the light, and the shadow of the longitudes and latitudes fall onto the celestial sphere. Imagine that it is able to produce a shadow there. Okay, so that projection is basically what you're going to call it as the equatorial coordinate system. So you will be able to see that here. So there is one particular line which is basically the projection of the Earth's equator onto the celestial sphere, which corresponds to 0 degrees. So anything which is to the north of it, it will be coming as 10 degrees, 20 degrees, 30 degrees, 40 degrees, like that. And once it reaches the pole, that will be corresponding to 90 degrees. Okay, the angles. Now if you go towards south, you will see that south of equator it will go as minus 10 degrees, minus 20 degrees, 30, 40, 50, minus 50 degrees, and so on up to 90 degrees in the southern pole, south pole, the projection of south pole onto the celestial sphere. Now in our case you are not able to see the south pole. This is the second homework assignment which I'll give you. Why can't we see the south pole from Bangalore? Okay. Now just to avoid confusion, let me just remove this equatorial coordinate system, which is the common coordinate system used by astronomers. We will study about this equatorial coordinate system in slightly more greater detail in one of the later lectures. Now I will create, or I will project only the equatorial, the celestial equator. You can see the blue line. Okay, this is the celestial equator, and I will also project one more great circle which is called as the ecliptic. Okay, this ecliptic is shown by an orangish line which goes like this. Okay, ecliptic is basically the path taken by the sun when it moves along the sky in a span of 1 year. Okay, so that means let's say today the the sun is at this point. After 1 month the position of the sun may be somewhere here. After 1 more month the position of the sun will be, I'm just rotating the screen so that the pointer will read it again. After 1 more month the sun may be here, and so on. Okay, so in a span of every month, sun approximately travels through 30 degrees along the ecliptic. Why 30 degrees? The total angle to be covered is 360 degrees, and there are 12 months in a year, so 360 divided by 12, which will work out to be 30 degrees. So in one particular month, sun is going to complete 30 degrees along the ecliptic. Now let's study a bit of astrology or associated things with that. Now if you have stars like this, or before that I have forgotten to mention one thing. Do you know what is the angle between the equator and the ecliptic? That angle is 23.5 degrees. Why? If you remember your geography when you were in school, which you have studied when you were in school, your teacher would have definitely told you that the axis of Earth is tilted with respect to the plane containing Earth and the Sun by an angle of 23.5 degrees. That is precisely the reason why the angle between the celestial equator and the ecliptic will be 23.5 degrees. Alright, now let's look at something called as the constellations. Now why do we need to have these constellations? That we will study in a later lecture. Let me just put on the pictures of the constellations so that you can appreciate the constellations here. So you can see that the one of the constellations which you are familiar with is the Libra. Libra is here. The Virgo is here, Virgo constellation, and one of the brightest stars in Virgo constellation is called Spica. You can see the star Spica, and so on. Now let me remove this artwork. Now if you look at the sky again, you will see that the path of the sun is what we are interested in. So I'll remove the celestial equator first and keep only the ecliptic. Now if you look at the sky, you will see that most of the planets, so-called planets, are very close to the ecliptic. For example, you can see the Mercury here. Okay, And if I remove the ground, let me just remove the ground, you can see the sun here on the ecliptic, and then you will see another planet called as Venus, which is very close to the ecliptic. And if I go around the ecliptic, you will see Uranus here, you can see the Mars here. Then let me just rotate it back so that I'll be able to move it around. So you can see the Mars, and if I go up again, you'll see Saturn, you'll see Jupiter, and so on. Okay, so all the planets which we can see, they are roughly close to the ecliptic. Okay, that is because most of the planets are lying in a plane which is close to the plane connecting Earth to the Sun. Okay, so they are all rotating about that particular plane, in that particular plane. Now, do you know what is the exact meaning of a planet? The planet is a word which has come from the Greek. Okay, it is actually in Greek is called, if I remember correctly, Asterili Planetae, which basically means the wandering stars. Why did the Greeks call planets as wandering star? That is what we are looking at now. So for the understanding that, let's look at one of the planets, whichever one you would like. Let's take the first planet which we see in the sky. The first planet we have seen in the sky is basically the Venus. Venus is the second closest planet from the Sun. So Sun is here and the planet Venus is here. Now I will center myself to the Venus and I will turn on the track of the Venus. That is, what we are going to do is we are going to speed up the whole celestial sphere and keep on observing only at the track of the Venus. So let me turn on the track, and now onwards I am going to skip 1 week every button press. So right now you can see that the date is 20th of June. If I press the button required, you will see that it gets shifted by 7 days. Okay, and in 7 days you will also see that the track is made. You can see the track. So you can see the track made by the Venus. So I am just skipping 7 days. Let's keep on observing it, the track. So the first observation you will make is that the Venus seems to be keeping on oscillating about the ecliptic plane. Now if you observe, do you see that the Venus actually went back a bit and came back? This is basically the reason why ancient Greeks told us that this is sorry, this is the reason, this looping is the reason why Venus was called as a planet. It's a wandering star. Now let's remove the tracks of Venus. Let's follow another planet. Let's look at Mars. If I put a marker here for Mars and I center the Mars and I will turn on the track. Now again I am going to speed up the days. So you will see, look at the tracks of Mars. So you can already see that the Mars is going backward, creating a loop kind of a structure and then coming back. So this is a common feature for every planet. So it will keep on going in the celestial sphere in one direction. Suddenly it seems to be moving in the backward direction, executes a turn and then comes back. Okay. Now right now if you notice, I have actually gone ahead in time. Okay, I have reached 2021 February 30th. So in this much period Mars has actually gone, executed a loop. Okay, this kind of motion by a planet, the going backward motion, is going to be called as the retrograde motion of the planet. and that is the reason why all the planets are called as wandering stars. So I will stop here for the day.